Module 2, Normal Distributions. Most of the statistical analysis presented in this module are based on the bell-shaped or normal distribution. The introductory section defines what it means for a distribution to be normal and presents some essential properties of normal distributions. The exciting history of the discovery of the normal distribution is also described in this module. Areas of normal distributions are described for calculating probabilities based on the normal distribution. A frequently used normal distribution is called the standard normal distribution and is described in the section with that name. A normal distribution can approximate the binomial distribution. The normal section approximation to the binomial shows this approximation. The normal distribution is the most important and widely used in statistics. It is sometimes called the bell curve, although the tonal qualities of such a bell would be less than pleasing. It is also called the Gaussian curve after Carl Friedrich Gauss, mathematician. As you will see in the history of the normal distribution section, although Gauss played an essential role, de Moivre first discovered the normal distribution. Strictly speaking, it is not correct to talk about the normal distribution since there are many normal distributions. Normal distributions can differ in their means and their standard deviations. Figure 1 is the normal distributions based on differing mean and standard deviations. Figure 1 shows 3 normal distributions. The green leftmost distribution has a mean of -3 and a standard deviation of 5/10. The distribution in red, the middle distribution, has a mean of 0 and a standard deviation of 1. And the distribution in black, rightmost, has a mean of 2 and a standard deviation of 3. These and all other normal distributions are symmetric, with relatively more values at the center of the distribution and relatively few in the tails. Take a look at this formula. The density of the normal distribution, which is the height for a given value on the x-axis, is shown below. The parameters, mean population and sigma, are the mean and standard deviation respectively, defining the normal distribution. The symbol is the base of the natural logarithm and is the constant pi. 7 features of normal distributions are listed below. First, Normal distributions are symmetric around their mean. Second, the mean, median, and mode of a normal distribution are equal. Third, the area under the normal curve is equal to 1.0. Fourth, normal distributions are denser in the center and less dense in the tails. Fifth, normal distributions are defined by the mean, symbolized by mean population, and the standard deviation, symbolized by sigma. Sixth, 68% of the normal distribution area is within one standard deviation of the mean. Seventh, approximately 95% of the normal distribution area is within two standard deviations of the mean. Take a look at this figure. The empirical rule tells you what percentage of your data falls within a certain number of standard deviations from the mean. 68% of the data falls within one standard deviation of the mean. 95% of the data falls within two standard deviations of the mean. 99.7% of the data falls within three standard deviations of the mean. The standard deviation controls the spread of the distribution. A smaller standard deviation indicates that the data is tightly clustered around the mean. The normal distribution will be taller. The larger standard deviation indicates that the data is spread out around the mean. The normal distribution will be flatter and more comprehensive. History of the normal distributions. The importance of the normal curve stems primarily from the fact that the distributions of many natural phenomena are at least approximately normally distributed. One of the first applications of the normal distribution was to analyze errors of measurement made in astronomical observations. Errors that occurred because of imperfect instruments and imperfect observers. Galileo, in the 17th century, noted that these errors were symmetric and that small errors occurred more frequently than significant errors. This led to several hypothesized distributions of errors, but it was not until the early 19th century that it was discovered that these errors followed a normal distribution. Independently, the mathematicians Adrain in 1808 and Gauss in 1809 developed the formula for the normal distribution and showed that errors were fit well by this distribution. This same distribution had been discovered by Laplace in 1778 when he derived the fundamental central limit theorem. The topic of a latter section, Laplace showed that even if a distribution is not normally distributed, The means of repeated samples from the distribution would be very nearly customarily distributed, and that the larger the sample size, the closer the distribution of means would be to a normal distribution. Most statistical procedures for testing differences between means assume normal distributions because the distribution of means is very close to normal. These tests work well even if the original distribution is only roughly normal. Areas under normal distributions. Areas under portions of a normal distribution can be computed by using calculus. Since this is a non-mathematical treatment of statistics, we will rely on computer programs and tables to determine these areas. Figure 3 shows a normal distribution with a mean of 50 and a standard deviation of 10. The shaded area between 40 and 60 contains 68% of the distribution. Figure 3 is the normal distribution with a mean of 50 and standard deviation of 10. Look at the figure. Figure 4 shows a normal distribution with a mean of 100 and a standard deviation of 20. As in Figure 3, 68% of the distribution is within one standard deviation of the mean. Take a look at Figure 4, which is the normal distribution with a mean of 100 and standard deviation of 20. The normal distributions shown in Figures 2 and 3 are specific examples of the general rule that 68% of the area of any normal distribution is within a standard deviation of the mean. Figure 5 shows a normal distribution with a mean of 75 and a standard deviation of 10. The shaded area contains 95% of the area and extends from 55.4 to 94.6. For all normal distributions, 95% of the area is within 1.96 standard deviations of the mean. For quick approximations, it is sometimes helpful to round off and use 2 rather than 1.96 as the number of standard deviations you need to extend from the mean to include 95% of the area. Standard normal distributions. As discussed in the introductory section, normal distributions do not necessarily have the same means and standard deviations. A normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution. Tables of the standard normal distribution often represent areas of the normal distribution. A portion of a standard normal distribution table is shown in Table 2. Table 2 presents a portion table of the standard normal distribution. The first column is the Z, while the second column is the area below. Take a look. If the Z is negative 2 and 50 hundredths, the area below is 62 10,000ths. For negative 2 and 49 hundredths is 64 10,000ths. Negative 2 and 48 hundredths is 66 10,000ths. Negative 2 and 47 hundredths is 68 10,000ths. Negative 2 and 46 hundredths, we have 69 10,000ths. Negative 2 and 45 hundredths is 71 10,000ths. Negative 2 and 44 hundredths is 73 10,000ths. For negative 2 and 43 hundredths, we have 75 10,000ths. Negative 2 and 42 hundredths is 78 10,000ths. Negative 2 and 41 hundredths is 80 10,000ths. Negative 2 and 40 hundredths is 82 10,000ths. Negative 2 and 39 hundredths, we have 84 10,000ths. Negative 2 and 38 hundredths is 87 10,000ths. Negative 2 and 37 hundredths is 89 10,000ths. Negative 2 and 36 hundredths is 91 10,000ths. Negative 2 and 35 hundredths, we have 94 10,000ths. Negative 2 and 34 hundredths is 96 10,000ths. Negative 2 and 33 hundredths is 99 10,000ths. Negative 2 and 32 hundredths is 102 10,000ths. The first column, titled Z, contains values of the standard normal distributions. The second column contains the area below Z. Since the distribution has a mean of 0 and a standard deviation of 1, the Z column is equal to the number of standard deviations below or above the mean. For example, a Z of negative 2 and 5 tenths represents a value of 2 and 5 tenths standard deviations below the mean. The area below Z is 62 10,000ths. To find the areas of the normal curve, the first step is to convert any given variable x into the standard score, z. The standard score z is the deviation from the mean x divided by the standard deviation, written as follows. Take a look at the figure below.